Hey class, I wanted to make a short video for you here on the last question on the homework. So we're asked to find the height of the atmosphere based on the air density of the atmosphere if it were A, uniform, so the same throughout, or B, linearly decreasing from a maximum at the ground to 0 at the maximum height. So for question A, we're going to just use our relationship that tells us the pressure at some lower elevation or location is going to be equal to the pressure above, P1, plus rho GH. And just so you know, for both of these, we're going to make a slight simplifying or important simplifying assumption that G is constant. So you could actually turn G into a function of height as well, but we're going to assume that it's approximately 9.8 throughout. So in this case, and really both cases, the pressure above your height of fluid is going to be 0 because at the very top of the atmosphere your pressure is going to be 0. So P1 will be 0 in both cases, and then P2, the pressure below, is going to be atmospheric pressure, 1 atm, or 1 times 10 to the 5th pascals. 1.013 to be more precise, 10 to the 5th pascals. So in this case then, if we wanted to find the height of the atmosphere if the density was the same throughout, then we would just get, since this is 0, the height of the atmosphere is just going to be equal to P2 over rho times G, where rho is this density and G is 9.8, and so you should be able to get the thickness of the atmosphere. For question B, then, however, it's a little bit different. We're going to use the same idea, P2 equals P1, which is going to be 0, plus now we're going to have to integrate from 0 to the height of the atmosphere of the, let's see, we'll do G times the density as a function of y, the thickness or height, dy. Okay, so in order to figure this out, we need a function for the density as a function of height, as a function of y. So if we think about this, to figure out our density as a function of y, we know that it needs to be at its maximum value when you're at sea level at y equals 0, and it needs to be 0 when y is at a maximum. So if we think of our density at sea level, which I'll call like density sub 0, which again is just going to be this value here, we need some function of y where that gets smaller as y gets bigger, and it becomes 0 when y is at this maximum h value. So I would just say, let's take that density and just multiply it by 1 minus y over h. So again, as y gets bigger, y over h will get bigger, and then 1 minus y over h gets smaller, approaching 0 as y approaches h. So again, you could also write this, if you would prefer, as being equal to the density at sea level minus the density at sea level times y over h. Again, that's just distributing the density, but you can see how it's going to be a linear decay as you get higher and higher. If we plug that in, then we can go ahead and solve. So again, P2, which is atmospheric pressure, is going to be equal to P1, which is 0. So that's just going to be equal to the integral of G, which is, again, we're treating as constant, the density, which is the 1.28 in this example, times 1 minus y over h dy, and then you can just integrate that function in order to solve. And so it's kind of interesting what you end up getting out of this integral, right? Since part of this, the first part is all constant here, you're just going to get G times rho initial, which you could actually factor out. Here, let's do it this way. G times rho initial, the integral from 0 to h of 1 minus y over h dy, right? So then what you're going to get here is G rho initial times the integral of the 1 is just going to give you h, and then you're going to get minus, let's see, you end up with y squared over 2h. Oh boy, this handwriting's sloppy. Let's try to make this a little cleaner here. I'm going to scroll up so I can try to write cleaner here. Okay, oh boy howdy. Okay, this is going well. So what we end up with here, again, is h minus, and then as we integrate, we're going to get y squared over 2h, and we're evaluating that from 0 to h, right? And so then what we end up with is simply g times rho initial times h minus h over 2, because again, you're going to get h squared over 2h. And so what you just end up with is g rho initial h over 2. And so then you can solve, and your h just becomes equal to, oh boy howdy, 2 times your P2, which is the atmospheric pressure, over rho initial times G. And what that is, if you notice, is it ends up being, since it's a linear decay, exactly double what it would have been otherwise. So anyway, I kind of solved the whole thing for you, but you still have to plug in your numbers. Try that out. I hope that helps you see how to use the integration over an area, and let me know if you have any questions.